This is Composite Materials, Lecture 12. And here we are going to be talking about some of the more recent developments regarding nanocomposites, recycling, etc. And we will also talk a little bit about how to present the data for these materials in a simple manner, which are called carpet plots. So that's what we will discuss in this lecture. So we looked a little bit about, we looked earlier regarding how the angle of the fibers, orientation of the fibers are going to control the properties of the composite by itself. You know that in simple terms you can use a rule of mixtures to calculate the modulus of the composite itself. But when you start changing the angle of the fibers from 0 degrees to, so you get the maximum value for the fibers, for the composite, when the fibers are in the 0 direction. As soon as you start changing it down to 0, you get almost close to the properties of the, so the fibers will probably not contribute much at all. So most of the time what we do is we have some fibers that are in the 0 direction, some fibers that are in the 90-degree direction, some that are in the 45 plus minus 45 or 60 plus minus 60, etc. So that you get almost uniform properties, because once you have the fibers all oriented in the 0-degree direction, you know that the composite is going to be a very non-isotropic material. So in order to overcome that, you combine the fibers in all different directions. So how do you make sure that the fibers are going to be, suppose you're using a method for infiltrating the matrix with matrix resin, infiltrating the fibers with a matrix resin, either as a gaseous mixture or as a liquid or a solid. So you want to make sure that there is enough permeability for the matrix to penetrate into. So again, these are going to, and this is represented in terms of S11 in terms of meter squared. So that is called the axial permeability, and the fiber volume fraction is going to control that. So suppose you are going to have about 40% fibers that has one of the highest permeabilities. But as soon as you start increasing the fiber volume content to 70% and 80% and things like that, you are going to have very poor permeability. And in the case of, as I mentioned to you, in the case of polymer composites, typically we like to have about 60 to 65% fiber volume fraction. Whereas in the case of ceramic composites, you like to have a permeability, a fiber volume fraction of around 35 to 40% maximum. So that's going to control how well you can infiltrate that bundle with a matrix resin or a matrix gas, etc. So what happens is that the fiber volume fraction is also going to control the properties, effective stress. So if you apply a stress and then unload that and do it all over again, it should typically, if the higher the fiber volume fraction, the better it will be as far as the first run and the second run. when you are infiltrating the fiber bundle with a matrix resin, you have to heat it in order to cure it. And what also happens is that when you heat it, the matrix viscosity also will decrease and it will start infiltrating, flowing very nicely, but then it starts thickening and gelling it. So above this temperature, the local chain motion, so it starts, the matrix resin will start creating crosslinks, and additional curing can also cause what is called higher amounts of cross-linking. So if you look at the cure cycle versus the temperature, you can see that when you start out, you may hold it at around 70 degrees F for a very short time. Then you start increasing it, you go to 240, you hold it there for maybe maybe about an hour or so, and then you hold it, you take it to 350 degree F and you hold it for maybe like 2 or 3 hours, and then you cool it down. Okay, and then you may also do some post curing in order to make sure that the cross linking is complete. And if you look at the viscosity versus temperature, you can see that you get the lowest viscosity around 240 degrees Fahrenheit. This is for the matrix 3501-6, and you can see that if you go beyond this temperature, after a while it starts cross-linking and becoming solid. So you need to have all the infiltration done by this time, and then you let it cure and become completely solid. So there are many, I mean, depending upon the uh, type of matrix resin system, you are going to have different viscosities, and the type of process also. So if you are going to have an RTM process, and you have about 60% fiber volume fraction or 70% fiber volume fraction, it will start reducing the resin viscosity, and then it will start becoming solid. But if you have a thermoplastic prepreg, you may have a solidification happening. The matrix resin will become liquid and it will start flowing nicely, and then you shut down the furnace so that it starts solidifying and becoming completely solid. But in this case, what you have to make sure is that you have to ensure that the matrix resin doesn't flow out and make the fiber bundles completely resin lean. You want to make sure that the resin stays behind inside the fiber bundle. So let's take a look at some of the design issues when you have multiple lamellae structures. So if you have fiber orientations in different directions, how can you, so what is a standard fiber lamellae structure? You can have fibers in the zero direction, one lamina, then you have another lamina that has the fibers in the 90-degree direction, and then so on. So this could be a simple way of representing a multi-layer lamella. And I think I also mentioned to you that the fiber bundles by themselves are in a matte form. So if you look at it from the top, this is how it is going to look like. But if you look at it from the side, so each bundle, so this bundle that is in this direction is this one. So it is undulating and going over and over the top and under the other layer, and these are the fiber bundles in this direction. You can also have um, interlacing through the thickness so that you get a better strength mat. You can also have that. But the most common one, especially if you are going to have a three-dimensional structure, you can have the fibers in all the three different directions. So this is what I would call a log pile type of structure. This would be the most ideal, but in order to create this bundle, fiber bundle, it is going to be extremely difficult. So the most easiest thing to do would be to go to have a mat like this and stack up those matted layers, one on top of the other with the fibers in different orientations. Because if because these have to be woven with the fibers bundles running in different directions. If that has to be the case, then it's going to be extremely difficult and expensive. So you don't want the composite structure to be very expensive if you have to make it something like this. And it may not always have the proper properties in all the different directions. It may have very isotropic properties, but the properties in certain directions may not be what you are really wanting it to have. So the most common one would be to have the lamella in with the fibers running in different directions. So this would be the so in this case this is a 0, this is a 90, this is the plus 45, this is a minus 45, and then you switch that and create a mirror image. So that would be minus 45, plus 45, 90 and 0. So this is actually written up as 0, 90, plus minus 45 symmetric, and this is not an isotropic, but they call it a quasi-isotropic layer. Okay, there is also something called an orthotropic layer where you have 0, plus 60, minus 60, minus 60, plus 60 and 0. So that is called an orthotropic layer. So when you calculate the properties using the Excel spreadsheet, you will find that if you have the fibers orientations in those different directions, they will have different kinds of properties, and you will have very uniform properties that are almost equal in all different directions, especially if it is a quasi-isotropic layer. So when you calculate that and you plot the data, so if you had the fibers all in the 0 direction, then you calculate the stiffness of that particular lamella, and then you compare that with the by changing the angle of orientation of the fibers, and you can see that. So for example, E11 for this composite would be, so if you had the fibers all in the 0 direction only, E11 is 138 gigapascals, so it's very high. But when you see the E22, you can see that it is only about 9 GPa, which is approximately what? about 15% of the normal direction. And then you can also see that G12 is 6.9 GPa, and you have a Poisson's ratio of approximately 0.25. So these are all based on equations that were described to you in the lectures a few lectures earlier. If you had the 090 plus minus 45 symmetric, you can see that these properties are totally different. They would start out with a lower um, elastic modulus in the E11 direction, but the E22 direction is almost close to that of E11. So you can see that if you have this, it becomes an almost quasi-isotropic material. So this is almost even, okay? But suppose you had 090, then it is not isotropic, but it is undulating and things like that. So E11 could be positive, E22 could be positive, uh, but then some of these properties might be negative also. So you can see that if you plot the properties of a composite depending upon the fiber volume fraction and depending upon whether it is continuously aligned or short alignment or random short materials, you can see that these properties are completely different. If you have continuous alignment, it gives you the best properties. If it is random short fiber orientation with the fibers in all different directions, you can see that it does not give you very high properties. So, and if you have a combination of the fiber orientations, then it would again change the properties. So you can see that if it is 090, then elastic modulus of the 090 would be half of volume fraction times the fiber modulus. If it is 0, then you get the best elastic modulus in the 0-degree direction. If it is continuous, if it is random orientation, then you are not going to have very good properties. So these are called, some of these plots, how you plot them are called the carpet plots. So you can plot the elastic modulus based on calculations, equations. You can calculate that and see how the properties are going to vary. And what you can do is when you make the actual composite itself, you can compare that. Even before you make the actual composite, you can calculate and see what kind of properties you are going to get for a combination of lamina. And then you can compare that with the property that you are getting actually. And then it tells you how good your processing has been and whether the processing has introduced any kind of defects or not. So depending upon the amount of 0-degree plies, you can see that the tensile strength will also increase. And if you have a combination of plus minus 45 plies, that will also change. Okay. Similar to the tensile properties and the elastic modulus and things like that, you can also calculate with the equations, you can calculate the coefficient of thermal expansion. And depends upon the material. So you can see that if you want to control the thermal expansion coefficient of the composite material, you can change the angle of orientation of the fibers and you can actually predict the properties and you can see how well the actual experiments compares that with the prediction. Now, when you actually make the composite itself after doing fatigue testing and things like that, um, you can do what is called contrast enhanced X-ray radiography. So what you do is you dip this material in a solution of iodine and you put that under an X-ray beam, and that tells you where the delaminations are, if there are any delaminations at all. And you can expose this to fatigue testing, and then you do the um, X-ray radiography again, and then it shows you where the fatigue cracks are. You can also have, especially if you have some kind of low velocity impact, you can have edge cracks in a laminate. And there could be severe damage due to those delaminations in this kind of a composite material. So if you have the 0 plus minus 45 90 degrees symmetric, you can have more delaminations. But if you change that to 90 plus minus 45 0, there could be less damage due to delaminations, because of the fibers preventing those delaminations due to the way the fibers are oriented. You can also have a hybrid composite where you have carbon fibers as well as glass fibers. So you can have a combination of properties for that. So if you have such a hybrid composite, you can actually calculate the specific modulus. What is specific modulus? Specific modulus is the uh, modulus divided by the density. Okay, so that tells you how good the properties are with regard to the weight of the component. So you can look at both. So A is for flexural modulus and B is for tensile modulus. So if you increase the amount of carbon fiber in the hybrid composite by weight percent, the more carbon fibers there are, it drastically increases the flexural modulus. But if the tensile modulus does not increase to the same extent as the flexural modulus. So the addition of carbon fibers have a greater effect on the specific modulus of a carbon glass hybrid composite material. Now you can also see that the properties of these materials in fatigue are going to be dependent on the properties of the fibers themselves. So suppose you had 100% carbon fiber composite, its fatigue limit would be approximately, in this case it would be about 600 megapascals. But if you started adding carbon fiber facings with a chopped glass fiber core, the stress limit actually decreases to less than 400 megapascals. And if you had only chopped glass fiber, then it is almost close to 40-50 megapascals. So the higher the amount of carbon fiber composite added to this material, the better the fatigue properties of your composite material. Now, shifting gears a little bit, so let me stop here and I will start this again in the next set of lectures.